The absolute baseline of a true total solar eclipse occurs during a highly specific window. It begins the exact fraction of a second the solar photospheric disk, the luminous, visible surface of the sun, is fully occulted by the moon. Astronomers define the boundaries of this window using two precise variables. Second contact, or C2, marks the instant of first internal tangency, when totality begins. Third contact, or C3, marks the end of totality, when the sun's surface begins to reemerge. Standard macroscopic eclipse predictions rely on a convenient geometric assumption. They model both the sun and the moon as perfectly symmetric, smooth spheres. Applying this smooth limb geometry to the physical universe yields built-in calculation errors. Relying solely on the mathematics of perfect spheres throws off predictions for C2 and C3 by several seconds. To understand exactly where the moon's shadow hits the Earth, astronomers use topocentric projections. A topocentric projection calculates the exact geometric line of sight from a specific, localized coordinate on the Earth's surface, rather than from the center of the planet. To achieve high-precision contact timings, we must discard the idealized mathematical sphere and map the exact rugged microtopography of the lunar limb. The edge of the moon is cratered and mountainous. As the moon advances, the sun's thin crescent breaks into isolated arcs of light passing through deep lunar valleys, a phenomenon known as Bailey's beads. These isolated light beams are a strict physical consequence of the moon's surface topography. Shortly before and after totality, observers frequently report the diamond ring effect. This intense point of light is often visible for 10 to 20 seconds outside true totality. The diamond ring is an optical artifact, not a distinct physical stage of orbital mechanics. As the Bailey's beads shrink, the remaining narrow crescent arcs output enough intense radiation to completely overexpose human retinas and camera sensors. Because standard optics are overwhelmed by this intense glare, visually observing the diamond ring cannot be used to accurately mark the exact physical onset of second contact. Watt's limb profiles map the peaks and valleys of the lunar edge. Deep valleys prolong the photosphere's visibility, allowing sunlight through after a smooth sphere would show full coverage. Conversely, tall mountains block the light beam, triggering second contact earlier. This rugged terrain dictates the exact position angle of the first internal tangency. A position angle is a standard angular measurement used by astronomers to locate specific points along the edge of a celestial body. The impact of this topography is highly sensitive to the observer's exact geographic coordinates. Moving just a few kilometers on Earth completely changes the relative alignment of the lunar mountains against the solar disk. Every single eclipse path requires a bespoke, mathematically intensive topographical correction tailored for the observer's specific latitude, longitude, and elevation. We can see the exact impact of this topography by examining calculations of NASA astrophysicist Fred Espenak for the 2001 eclipse in Zambia. The smooth limb prediction placed second contact at 1309:13.3, but applying the topographical correction reveals a mountainous area that physically occulted the photosphere 3.5 seconds earlier. Rugged topography on the trailing edge also triggered third contact 5.4 seconds early. Factoring in both limb corrections, the topographical reality resulted in a net totality duration 1.9 seconds shorter than the idealized calculation. Macroscopic predictions provide the general path, but the physical timing of an eclipse operates strictly on the microscopic terrain of the moon. This introduces a severe observational challenge. If the diamond ring artifact overexposes optics for up to 20 seconds, it obscures the exact millisecond of tangency required to empirically verify a 3.5-second limb correction. Standard videography and photography are useless for this specific level of verification because the glare destroys the edge data. Eclipse researcher Robert Slobbins bypasses the glare entirely. Instead of attempting to view the photosphere directly, observers record the solar spectrum. This schematic illustrates the necessary hardware setup, a camcorder fitted with a diffraction grating filter. A diffraction grating is an optical component that splits incoming light into its constituent wavelengths, creating a visible spectrum. As long as any fraction of the photosphere remains visible, the camera records a continuous spectrum of light. By forcing the incoming light into a spectrum, the overwhelming glare of the diamond ring is dispersed. This allows observers to isolate the exact physical moment the properties of the light change. The precise moment of second contact occurs the exact millisecond the continuous spectrum of the photosphere completely vanishes from the sensor. What remains for a few fleeting frames is the flash spectrum. The flash spectrum consists of discrete emission lines produced by the solar chromosphere, the thin layer of the sun's atmosphere situated just above the photosphere. This simulated feed shows the methodology in action, strictly synchronized to a GPS time signal. Post-eclipse, observers scan the 29.95 frames per second footage until the continuous spectrum abruptly collapses into discrete emission lines on a single specific frame, locking the exact timecode. Identifying this exact frame yields an empirical second contact timing accurate to fractions of a second, completely bypassing the optical illusions created by standard lenses. As this visualization demonstrates, the boundary of the moon's shadow traveling across the Earth is not a clean, geometric cone. It is a jagged, highly complex edge dictated entirely by the specific topographical geometry of the lunar surface. Visual phenomena like the diamond ring are functions of instrument resolution, sensor exposure, and diffraction. They are artifacts, not physical milestones. True precision demands empirical verification through spectral videography, stripping away the glare to measure the actual physics of the light. Understanding the mechanics of an eclipse requires merging macroscopic orbital modeling with microscopic cartography, proving that the scale of cosmic events is governed by the smallest physical details.